The charges are enclosed by this surface. It has two ends. So this is end 1 and this is end 2. And this will help us in the flow of electric field, that is electric flux is contributed by two ends. What is Q? We know from surface charge density, that is sigma is equal to Q by A, charges per unit area. What is small r? Small r is nothing but the radius of Gaussian surface. So electric field is always directed outwards. Hello everyone, welcome to session 6 of chapter 1 Electric Charges and Fields. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in the previous session, we were studying about the Gauss law in electrostatics. The Gauss law states that the total flux in an electric field is equal to 1 by epsilon naught times the charge enclosed by it. And we have even learnt one application of Gauss law. And in today's session, we are going to learn few more applications of Gauss law. So we have studied about the Gauss law application in case of uniformly charged wire. And in today's session, we are considering an infinite plane sheet which is charged with the help of Gauss law. I have considered an infinite plane sheet as a Gaussian surface where the surface is covered with a charge density sigma. So the charges are enclosed by this surface. It has two ends. So this is end 1 and this is end 2. And this will help us in the flow of electric field, that is electric flux is contributed by two ends. Now let A be the area of Gaussian surface, sigma is uniform surface charge density, and we all know what is Q, that is charge enclosed by the Gaussian surface. Here what is our Gaussian surface? It is rectangular parallelopiped. So we have considered a rectangular parallelopiped Gaussian surface. We all know what is Gaussian surface. I have told you in the previous session, it is an imaginary surface where the Gauss law is applicable. So from the figure we can see that only phase 1 and phase 2, the two phases at the ends are contributing to the electric flux. So the electric flux from phase 1 plus electric flux through phase 2 gives rise to the total electric flux phi. So that is equal to E into A. So flux phi is equal to EA, that is the flux through phase 1 plus EA, the flux through phase 2. Now we are adding these two and we get phi is equal to 2 into EA. Here flux through both the surfaces are equal. So now this is the expression for electric flux, as we know what is flux, how to define flux. Now let us apply the same Gauss law for this condition, and from Gauss law we know that phi is equal to Q by epsilon naught, that is 1 by epsilon naught, the charge enclosed by it, that's Q by epsilon naught. So now what is Q? We know from surface charge density, that is sigma is equal to Q by A, charges per unit area. So from this we can write Q is equal to sigma into A. I am substituting the same in the above expression, and phi is equal to sigma A divided by epsilon naught. That's my equation 2. In this expression, sigma is a surface charge density and A is the area of the surface where we are observing the charges. So now we can compare these two equations, equation 1 and 2. You can observe this equation 1, we have phi is equal to 2EA, and equation 2 we have phi is equal to sigma A divided by epsilon naught. So in both the cases the LHS is same. Let us compare the RHS now by equating them, that is 2EA is equal to sigma A divided by epsilon naught. A and A will get cancelled and E is equal to 2 will come to the denominator, sigma divided by 2 into epsilon naught. So in vector form we can represent the same by adding the unit vector, that is E is equal to sigma divided by 2 into epsilon naught into n cap, where n cap is a unit vector. As we all know that unit vector helps us in finding the direction. So let's move on to the next condition. Let us now find the electric field or electric intensity due to a uniformly charged thin spherical shell by applying Gauss law. So this condition at three different scenarios we are observing, that is a point outside the sphere, a point on the sphere, or on the surface, or a point inside the sphere using Gauss law. So now these are the three different conditions we are taking. That is, you can observe here we are considering a sphere as a Gaussian surface. So you can observe here it's a P is a point which is outside the Gaussian surface or outside the sphere. So in this condition O is the center of the sphere and R is the radius and Q is the charge enclosed, P is a point outside the charged sphere. You can observe the dotted lines represents the point which is there outside the charged sphere. But in this case, you can observe here is my point P. So, on the sphere or just outside the surface I can say. And in this case, P is considered inside the sphere. So, these are the three conditions for a charged sphere where we are finding the electric intensity or electric field outside the charged sphere, on the charged sphere, inside the charged sphere. With the help of Gauss law, we are going to find the electric intensity. So, this is another application of Gauss law. So, let us now find for the first condition. You can observe here, sigma is the charge density or the surface charge density. We know on this surface the charges are enclosed. So, sigma gives us a surface charge density. So, we have considered a spherical shell of radius r. You can see here, this is a spherical shell of radius r. So, sigma is the surface charge density. You can observe P. Let P be a point outside the sphere or outside the shell. So, what is the Gaussian surface we have considered here? That is sphere. So, what is small r? Small r is nothing but the radius of Gaussian surface. So, electric field is always directed outwards because we have considered positive charges on this spheres. So, it is radially outwards. So, now let us assume this Gaussian sphere is divided into small parts, that is delta S. Let area of the small parts of this Gaussian surface be delta S. The surface elements, small surface elements, that is delta S. We know what is the expression for electric flux, that is delta phi is equal to E into delta S cos theta. So, here E and delta S, what are the elements we have divided? That delta S elements and the electric field are parallel to each other. Since they are parallel to each other, theta is equal to 0, and what's the value of cos 0? It is equal to 1. So, now if this value becomes 1, I remain with delta phi is equal to E into delta S. So, total flux through the Gaussian surface is sigma is equal to E into summation of delta S. Why this summation of delta S? Because we have divided the Gaussian surface into n number of small parts. Now, I have to find the total electric flux throughout the surface, and hence it is summation of delta S. So, when you add all these small surface area element, we will get the total area, that is phi is equal to E into A. What is the area of this Gaussian surface? What we have considered is sphere. So, area of sphere is 4 pi r square. So, phi is equal to E into 4 pi r square. That's my equation 1. So, now we have got the expression for electric flux. Now, let us apply the Gauss law. So, what is Gauss law? It states that phi is equal to Q divided by epsilon naught. But what is Q? According to surface charge density, sigma is equal to Q by A, and Q will be equal to sigma into A. So, let us substitute the same thing here. So, what we get? Phi is equal to sigma into A divided by epsilon naught. What is A? Area of sphere, that is 4 pi r square divided by epsilon naught. Now, I got the equation 2. Equation 1, LHS is phi. Equation 2, LHS is phi again. So, let us compare these two equations, and we get the RHS term we can equate, that is E into 4 pi r square from equation 1, which is equal to sigma into 4 pi r square by epsilon naught. So, now what are the common things that we can cancel out? That is 4 pi and 4 pi we can cancel, and we remain with E into r square, which is equal to sigma r square by epsilon naught. So, but we know from surface charge density, sigma is equal to Q by A, or it is Q divided by 4 pi r square. So, if I substitute in the place of sigma, Q divided by 4 pi r square, I get the equation E equals Q by 4 pi r square into r square divided by epsilon naught into small r square. And also we can write this expression as E is equal to, by cancelling this r square and r square, Q divided by 4 pi epsilon naught r square is the expression for electric field outside uniformly charged sphere. So, let's move on to the second condition now, that is electric field on the surface. So, look at this diagram carefully. So, we have a spherical surface with center O and of radius r. Let P be the point on the surface. If I consider the surface is covered by a charged particles, or it is enclosed by a charged particles. So from this previous expression we have E is equal to Q divided by 4 pi epsilon naught r square. So for a point which is there on the surface, now the radius of Gaussian surface is equal to the radius of the point where it is located. In that condition, r, small r is equal to capital R. So we can replace the small r square with capital R, and we get E is equal to Q divided by 4 pi epsilon naught into R square. So now we know what is Q. From surface charge density we know sigma is equal to Q divided by A. So from this we can write Q is equal to sigma into A. What is A? A is area of the sphere, that is 4 pi R square. So now let us substitute in the place of Q sigma into A, that is sigma into 4 pi R square divided by 4 pi epsilon naught into R square. So we'll cancel 4 pi and 4 pi, R square and R square. We remain with E is equal to sigma divided by epsilon naught is the expression for electric field for a point on the surface of the sphere. So the next condition is electric field inside the shell. So look at this diagram now. I have a spherical shell where point P is lying inside the sphere. Inside the sphere. So let us now understand the diagram properly. How to find the electric field inside the shell? At point P we need to find now. So in this figure we have the electric field, it is radially outwards. E is the electric field and R is the radius of the spherical shell and small r is the radius of Gaussian surface. So now here the Gaussian surface, whatever we have considered, is a sphere or spherical surface. So P is the point which is there inside the shell. What is the flux through the Gaussian surface? That is phi is equal to E into A. So A is nothing but the area of the spherical surface or the sphere, that is 4 pi R square. So we get phi is equal to E into 4 pi R square, that's equation 1. So in this case, the Gaussian surface encloses no charge. Here there is no charge because the charges are on the surface. So when there is no charge, Q is equal to 0. So we know from Gauss law, phi is equal to Q divided by epsilon naught. So when Q is equal to 0, the entire phi will become 0 because 0 divided by anything is equal to 0. Now we can compare the two equations. That's from equation 1 we have phi is equal to E into 4 pi R square, and here we have phi is equal to 0. So E into 4 pi R square is equal to 0. We need the expression for electric field, and hence let us bring this other terms, that is E is equal to 0 divided by 4 pi R square. So let's bring 4 pi R square to the denominator, and 0 divided by anything is 0. So we can say that when there is no charge or when Q is equal to 0, electric field is equal to 0. So the conclusion is the electric field strength inside a charged spherical conductor is 0. So these are the applications of Gauss law, and all these three derivations are very important examination point of view. We can expect this for 3 marks. So this is all about electric charges and fields. So in this chapter we have learned so many basic concepts and properties regarding electric charges, fields, and the laws which are applicable to find electric field intensity, Gauss law, its applications, and many more things. So see you all in the next session with a new chapter. Until then, keep learning all of you. Thank you.